So I'm just going to start. I'm a scientist at the National Center for Atmospheric Research, and I have just recently transferred over to the Research Applications Lab inside NCAR. My boss is sitting back there, Lawrence Bouja, in the Climate Science Applications Program. And the reason is, for a long time we have worked on the science itself, on developing and explaining and further improving models, working with new data and so on. The fundamental problem, as both of the speakers mentioned before, the fundamental problem about climate change is solved. We do know what is causing the warming that is happening. We can prove it, we can show you, we can walk you through. What is not really known is what we should give Representative Tyler as a suggestion what exactly he has to do in planning for the next 10 years, for the next 20 years. So while we understand the climate system on a global basis, at the scale in terms of time and space that is actually informative for a representative, for you with your business, for individuals, at that scale these climate models are not yet ready to answer your very specific questions. And that's why I'm really happy to have transferred into this group, Climate Science Applications, where we try to make that jump. We try to say, here is all the science, but you come to us, we come to you, let's work together. What are the elements that we can tell you? What are the elements where you have to be very careful in taking climate model output, for example, that make predictions? There is a fine balance, and it only can be in a constructive way moving forward if we really sit together at the same table. And that's the trend of the science that I would like to support and that my boss back there, Lawrence Bouja, has initiated inside NCAR. That is what we now need to do. And I try to convince you, if you can actually see it, we will see what is the science argument and what are the outlooks from that. So let me walk through. There are different ways how you can study climate. Ways of studying climate. You can look at observations, weather or climate. You can look at output from an airplane or measurements from an airplane, from satellites, from stations on the ground. Or you can look at past information, geologic information. That can be from the last few hundred years, from ice, from pollen that you have in your lake. It can be in sediments that are hundreds of millions of years old. What they represent is the conditions under which they either grew or were deposited, and you can make certain deductions from analyzing these conditions. Now, in the background, as you saw with the exercises before, with these observations and with our knowledge improving, theories have developed, theories that describe why you would expect certain things to follow if something is happening. The sun goes up in the morning, and from experience, you recognize the energy from the sun is going to warm up, and all of that, what follows. This can be put into a very simple model, and when we talk about the climate system nowadays, we have to use very complex models. Complex models, not in their fundamental principle, because even in the most simple climate model, the summer is going to be warmer than the winter. That is not a difficult thing. Weather is very difficult, and we can't predict it beyond 14 days. That is a mathematical impossibility to go beyond 14 days. Yet the summer is going to be warmer than the winter. That is a fundamental, much slower process. And what the system is what we call a damped oscillator. It's an oscillator that has chaotic behavior, but if you push it, it's going to respond to it. And when summer comes, it's going to get warmer. So climate models, they have the chaotic behavior of weather, but then they respond to the changes in the boundary conditions, the climate boundary conditions, what drives fundamentally climate. And we have learned, if we just look at the atmosphere, we're missing a lot. We have to include oceans. When we have the oceans in there, we still don't have the land surface that responds to the vegetation, hydrologic cycle. With that, we come to sea ice, we come to glaciers, we come to the carbon cycle, and all of these features are now being built into a single climate model that evolves in time and is driven by certain assumptions or observations of boundary conditions such as greenhouse gas concentrations, changes in the locations of the continents, as we heard in plate tectonics. The same model can be used for a completely different configuration. And as we saw before, the fundamental way how we explain the result of the model, what we expect it to produce, is exactly the same way of transferring that knowledge into an expectation, if it's 100 million years ago, a state of the Earth, if it's for present day, or if it's for the future. The physical explanation linking the boundary conditions to the response should be exactly the same. A key thing that I would like to throw up at the beginning here is also, when we're talking about global warming, climate change, there are many different understandings about these terms. I want to be clear what I understand about. Global warming is observed with station data, and furthermore, you come towards the present with a huge array of instruments from space, from the ground, below the surface, and so on. And what is the fundamental global record is about 150 years long, and as you can see, it has warmed up from the left of about 1850 to present. It has ramped up over the 20th century. Yet what we are referring to as the signal of climate change, of global warming, the actual warming, it's really the last few decades of this. There is not a need to explain every single fluctuation on this curve with just greenhouse gases. Where we have identified and where we can put the finger on the cause is in the last 3-4 decades of this curve. And just recently, the first estimates of 2010 are in. 2010 is going to be very close to be a new record, again extending this overall growth, this overall increase of the temperatures. And it's again the end that is referred to. And if you could read this up there, there's the key sentence from IPCC. IPCC is the Intergovernmental Panel on Climate Change. That is a summary of all the available science. The last report was published in 2007. And it's really that it's highly likely that the end of the 20th century is primarily driven by greenhouse gases. And that's what global warming as an overall signal is. Climate change has then many aspects in hydrologic cycle, in clouds, in soil moisture, in nutrient availability, in carbon fertilization of plants, for example, and so on. The goal of climate research, again, this is going to mirror a few of the statements before. The key really is when geologists, climatologists, meteorologists, and philosophers sit together, there needs to be a seamless explanation of things. It cannot be that one time period has different laws that explain things than a different time period. The same processes that operate over hundreds of millions of years also operate from day to day. The changes are probably relatively small compared to 100 million years, but it's not fundamentally different. It has to work. It has to be a seamless explanation through time and space. A system we have to look at that captures forced fluctuations, so the summer that is driven by simply the angle of the sun, versus random weather fluctuations, or year to year, which is internal to the system. Internally, the climate system has oscillation capability. It doesn't change fundamentally that there's forced fluctuations and then there's variability. The combined signal is what we are actually seeing. And at the very end, of course, we can be relying on tools, or we can better rely on tools if we have a solid framework that allows us to make predictions. And predictions don't only mean in time into the future. Predictions can also mean if we would now put a satellite in space that measures the temperature in the uppermost atmosphere, something we have not reliably done with rockets, for example, here is what we would expect to find right now. That's a prediction in space, not in time. We can also do predictions in time. So a solid framework allows to make these predictions, and we can constantly test it. Now, if Sherlock Holmes, which my son is starting to read this, that's why I come immediately with these examples. If Sherlock Holmes has to reach a conviction or to find a culprit and he has to prove it, there's a number of things that the process of finding the cause or the culprit have to go through. There has to be some sort of a suspect or many suspects. We look for certain motives. Why would one do that? In itself, that might not be enough, but there could be fingerprints or DNA analysis nowadays, something that really ties a particular suspect to a signal. There can be all sorts of other clues around that corroborate, that are consistent with the arguments that are already there. And we have to make sure that there's no alibi. We have to make sure that we know it's possible that that suspect, who then fulfills all these different other points, was not proven to be somewhere else, and therefore could not have been there. In science, for climate change, we do the same thing. We call it detection and attribution. Detection is we identify that there's something happening. And attribution is where we try to say, what is the primary driver? As a suspect, we use the different factors that we know can modify the overall energy balance, and with that, the heat of the surface climate. As motives, we use processes. How do they do that? Why do they do it? What do we understand about this? And then fingerprints, if a particular factor is operating, it will have its very specific effects in space and in time, because it changes in time and it changes in its spatial effect. So we should be able to do something like DNA or fingerprint analysis. And then there are many multiple lines of evidence that say, yes, this is really a crime, something is happening, that have nothing to do directly with the cause itself, but are a response. The system is indeed recognizing that something is happening. And finally, we have to look constantly for counter evidence. Could all the things that we have observed also be explained with something else? If that could be brought forward, then an identified suspect could possibly have an alibi, or would not be the only cause. So let's move forward, and I'm going to run through some of these suspects and show you where we are with knowing this on a global basis. So here's a bunch of the primary drivers that we are aware of. Of course, the sun, and Chuck is going to talk later about a little bit more about the sun, and I took most of it out in this presentation. Of course, the sun is a suspect that it could modify climate. A small change in that input should have an effect at the surface. But it could also be the ocean. Ocean fluctuations, oceans contain a very large amount of heat, and it could simply be heat coming out of the oceans that warms the lower part of the atmosphere where we are living. It could be volcanoes, people have claimed, yet it's relatively difficult to come up with a way how volcanoes would warm up rapidly. We can come up with many ways how volcanoes can cool down, but warm up is a different thing. Yet this is out there too. And then there's man. And maybe an alien's unknown process that is just now arriving on our planet, but has never operated and has never visited. But I don't think this is going to be a key suspect here. So let's move on. And first of all, many people are surprised in saying man is such a small operator on this planet. And they don't recognize that we, with our actions, reach every part of this planet. Carbon dioxide in the atmosphere, which has been measured since the International Geophysical Year in the late 50s, is one indicator how through the atmosphere we can reach every point. South Pole measurements or Hawaii or Greenland measurements show the same trends. In the oceans, there's a map on the right that shows you pollution levels, fisheries effects, with the darker colors in orange and red as being higher human impacts. You see there is barely a remote location on the planet that is not affected by humans. We reach every part of the planet. The green colors are the least affected, and this is simply where water comes up from the deeper parts of the ocean, and that has not seen human civilization interacting with it so far. but we reach every part of the planet, we should not be surprised. The basic physics of greenhouse effect, when we change greenhouse gases, is very simple. We see that at the surface we are emitting heat. The planet has to get rid of all the light and heat that comes from the sun, and so it radiates away in the long wave. And what actually exits on top of the atmosphere, this is the smaller arrow above, is simply less than the energy that goes away from the surface. So somewhere in this atmosphere, that radiation gets absorbed and re-radiated. And the more gases, greenhouse gases we have in the atmosphere, the smaller the amount of outgoing radiation, and therefore greenhouse effect is happening. It's a very simple principle. It's known since 120 some years. There is no physics argument anywhere in sight that would say that this is not true. Here are calculations of all the different greenhouse gases and how strongly they affect this exchange or this buffering of outgoing long-wave radiation. And as Doug mentioned earlier on, CO2 on top there is a little small on this screen. CO2 is by far the largest component of the gases that cause warming. There are a number of other gases, particularly methane and ozone as well. But then there are some aerosol. Have you looked over the city here on a summer day? You see the brown cloud. You see it particularly close to the power plants or the refineries where there's sulfur in there, where little particles reflect sunlight back into space before it can reach the surface and before it can heat up the ground. These are these blue bars that go to the left side, which are also human-made, but they actually cool. The combination of these factors all together are then in the lowest bar there, that red bar that goes towards the right, that says all of these factors together are warming this planet. The one natural factor that is in there is the second from the bottom, is solar variation. And we have measured that since 30 some years now. There's no trend. In fact, the last solar minimum was the lowest we've ever measured. So there could be a contribution, but it's probably very small. Let's look for fingerprints, DNA. And one that is my favorite, because it drives it home for everybody, and anybody who would come up with another suspect better work with this graph. So if we look at the planet, we have the surface, and on the left side, some sort of a cartoon of how our atmosphere that goes up and down into the ocean. If it were really just internal climate variation, cycles, geologists and other people like a lot of cycles, and cycles do happen, absolutely, on all time scales. But we can't invent and create energy. So we have to work with the available energy. If a cycle happens that moves heat, energy out of the oceans and puts it into the atmosphere so that we see warming in the atmosphere, what we should see is the lower part of the atmosphere, this lowest line here, that would be our surface, and it would be heat that comes out of the ground and is pumped into the lowest part of the atmosphere and warms up. The higher up you go, you lose more and more of that heat. Some of it goes to get dissipated and so on. But what is key is below the ground, where that heat has to come from, it has to cool. Otherwise, energy is not conserved. You can't generate energy out of nowhere. That would be the signal if it's internal variation. The second thing, volcanoes. Volcanoes explode. Mount St. Helens was mentioned this morning. You put into the stratosphere a layer of these particles, little droplets, ash as well. Sunlight wants to come in but gets reflected. Part of it gets reflected back out. You warm up. In that layer where this ash or these particles are, it warms. But underneath, there's less sunlight coming down. Therefore, when you look below that layer, everything should cool, if it's volcanoes. If it were the sun, the outermost exposed layers of our atmosphere, they feel immediately when the sun changes. Every 11-year cycle, even a solar flare, we see the changes high up in the atmosphere. And it should go all the way down towards the surface. When the sun increases its output, everywhere it should be an increase in temperature. But the closer and closer to the surface you come, the smaller the signal gets because there's some absorption above. And when you come into the ocean has a huge heat capacity. It takes a lot of change to change the temperature of the ocean. So it's a very small signal, but everything goes in the same direction. If you use greenhouse gases trap energy, the heat from the surface, in the lowest part of the atmosphere, and essentially, to simplify it a bit, prevent it from warming up the upper part of the atmosphere. That's what this greenhouse effect does. So these are the four culprits, and here are the observations. And these are observations. Every line here is independent. There is no conspiracy between these groups. This is a measurement from a satellite, but we can use radiosondes. We can use rockets. We can use satellites here up on top. The orbit of satellites actually change because the upper atmosphere is compacting, because it's getting colder. That was one of the effects of the Galilean thermometer. Engineers that have to correct for satellite orbits, they say it's because the upper atmosphere is cooling. The lower part of the atmosphere and the surface, the oceans, we know it. The ground, from geologists that have drilled down, put boreholes into the continents, we see a change in the temperature in the borehole that is positive. This is your proof. There is no other way to generate the multitude of trends other than with greenhouse gases, and greenhouse gases seem to do it really well. So, do we need to explain all the variations with greenhouse gases at all times? No, that's not the case. When you go back particularly into the past, where greenhouse gases might have been a feedback, glacial interglacial fluctuations that come because the orbit changes, because the Earth changes its way, how it goes around the sun, the carbon cycle is connected to this and operates as a feedback. However, if there are natural bursts of carbon coming out into the atmosphere, suddenly it's a driver. It changes that balance between climate and the carbon cycle, and therefore it pushes. It can be a driver. We are doing this right now with our emissions. 3 scales of effects that are precipitating from this overall warming. At the very smallest scales, any individual point, Denver, Boulder, a mountain resort, it's very hard to identify the trend because year-to-year fluctuations can be substantial. And so a record year shows up, everybody says, oh, it's warming, and then a negative record shows up. And so suddenly, no, it's cooling. So it's at the smaller scale you go, it's very hard to separate overall trends from that internal noise that is there. Yet in one particular element, we have managed to detect the fundamental change. And it's not in the mean, but it's as you go to the extremes of certain events. And in one particular thing, precipitation operates very sensitively to fundamental shifts of a distribution. And so the extreme precipitation has already been observed in many locations around the world to have increased. So when it rains, it might rain less in some areas, but when it rains, it's going to start to rain harder. And that's simply due, when you have a warmer atmosphere, it can carry more moisture, and in effect, it's an exponential increase. The warmer it gets, more moisture can be carried, and therefore, when it really rains hard, exponentially, it's going to come down really hard. That's one signal at individual stations. More a little regionally, mountain glaciers around the world are melting with a few surging. Some say because in a few locations there's more snowfall in the accumulation zone. In other places it's because the ground is getting warmer and therefore the ice is shooting forward a little faster. So glaciers around the world on the regional scale. And then again on the global scale, one other factor that is connected to warming is the ocean takes up most of that energy that we keep inside the system with greenhouse gases. So more than half of the global sea level rise is simply due to the warming of the upper part of the oceans. A second component is the melting of the glaciers, and the last one that is a wild card, how much are the polar ice sheets contributing? I've only now started to get tools to measure how at the edges the ice is melting, yet in the interior, which is very high and very cold, there seems to be an additional accumulation. But what happens when we keep warming up? Could there be a potential rapid feedback from the polar ice sheets to that overall sea level change? And sea level change here is continuous. Just a couple slides that are very famous for sea ice, and particularly summer sea ice. In winter, when there is no light at the poles, you can always rebuild surface ice. It's very thin, but you can cover a large area with sea ice. But in summer, the thinner that sea ice was from winter, it's very rapidly removed. And therefore, you get prone to have less and less and less ice the warmer the overall system gets, even though in winter it's going to come back. This was in the year 2000 up there, and a model study predicts what the year 2040 even looks like. Some models say it could already happen in 2020, which is the summer sea ice distribution over the Arctic Ocean. It's a little dark here, but you can see there's sea ice left in the Canadian archipelago and maybe bundled up a little bit against Greenland. And that just depends on the winds. But fundamentally, that Arctic Ocean is going to lose its sea ice, and it's going to lose it very soon in the summertime. Transportation industry is already betting on this. They're building ships that can go and steam through that Arctic Ocean, even if some winter sea ice that can get maybe up to a meter thick is still present. They're building ships that can go through. Right now, the white part in this is 2 to 3 meters thick. That's not navigable. At the bottom, the trends, what models do versus the observations. Whoops, where am I here? Observations, and I put in 2010, which is continuing the overall trend. It seems to be a little faster than the models. More or less, the key is there can be jumps, but the trend is very clear. So if you take all these individual clues, can you convict on an individual clue? No. Because every measurement has errors, has some uncertainty, there are short records, and all of this. But what about the combined? Have you ever played with combination theory or so? When you say, how likely is it if I have 10 different measurements, all 10 fit with the overall pattern of greenhouse gases, but there is something wrong with these measurements? So you take a dice with 6 sides and say, what's the likelihood of 10 times throwing a 6? When you combine multiple records, even though each one has some error, uncertainty, it is very hard to produce a physically consistent picture. And that's, from my opinion, the absolute proof that there is no way that any other of these known other culprits can explain the observed warming. Is there an alibi? Does anybody know something that could come forward that says it could be something else as well that fulfills and can explain all these patterns? Not that we know of. There's not a single stream of data that says. The only thing that comes up is, well, it's in this measurement and that measurement is uncertain. But nothing says I can explain all of the observations and here's the process. It doesn't exist. The fingerprint is there. We have a 3D structure of a greenhouse signal that is observed with multiple types of instruments, independent from each other, corroborating each other. We have it in the oceans, at the surface, and we see the cooling high up. There are spatial patterns associated with it. The fluctuations, if it were the ocean that is producing this heat that is coming out, because there's no other location where it could come from, we would see it. It's not there. So a few follow-ups now. Given all this knowledge and given the process understanding that we have developed with observations, let's look at a couple models. And very briefly, just to give you an impression what these models nowadays look like. Climate models are essentially taking a way of describing the Earth's climate system, again, with the oceans, with the ice, with the land surface, the atmosphere, all of this, the vegetation, and now ice sheets as well, all together, and they describe how individual locations are exchanging energy momentum with its neighbors. How the sun goes up in the morning and how the warming at the surface happens, and all of that comes with it. the annual cycle. You see the breaking down of the world into small little boxes, and the more advanced we are, the smaller and smaller the boxes get. And down here you see what North America looks like in the last round of IPCC of these simulations. You see a big ridge here in the west, the big plains, a cartoon-like representation of the Great Lakes. And luckily Florida is there, but the Baja California is a little odd. And that's simply because of mathematical constraints. If we want to use a model output, so for Colorado, for you, to say, can I use a map for Colorado that tells me exactly what's going to happen in one location, be really careful, because it's not the same world as you are dealing with out here. It's a smoothed world. A little dark, a movie that shows you that if you look at a climate model simulation and you put next to it a satellite loop from the real world, it is very hard to see the difference. And depending on how I choose colors, you cannot pick which one is real and which one is simply the model. All this should indicate is the complexity of these models has increased to a level that is stunning compared to just a couple decades ago. And here are just a few observations. Up above is the model. At the bottom is the observation for the annual air temperature at the surface. And the only thing that this model knows is not a single measurement from out there. It's only inside the computer. There's not a measurement that goes into a model. It's internally simulated. Here is the fluctuation from year to year, the primary fluctuation that is driven mostly by El Nino. Fluctuations internally in the model and in observations. It looks pretty similar. Models behave not only in the average, but also in their fluctuations, more and more realistic. Now we can play with a climate model, and we can use particular drivers. We can use the natural factors, solar variations, or volcanoes. We can use all forms of possible anthropogenic drivers, greenhouse gases, aerosol, or ozone fluctuations in the stratosphere, all this. And we can do it step by step or all together. In a model, you can play. What if? Here is a study, what if? And first, look at the black line, which is right in here. The black line is the observed global temperature for the 20th century. The red area is an area that is covered by 4 different simulations with the climate model with different weather, but climate evolving when all of the drivers, natural and anthropogenic factors, are included in that climate model, in their history, concentration of greenhouse gases, solar variations, volcanoes, and so on. The blue range, however, ignores all of the anthropogenic factors and asks the question, how much of the 20th century could we possibly explain with just natural factors? And you see, up to about the 1960s, natural factors are not far away from the black line or the red. But afterwards, this is what I referred to at the beginning, that separation, that signal of global warming starts somewhere in the 1960s, 70s. That's when these expected curves separate. And that warming, that difference between this blue range and the red range, that is anthropogenic global warming. We can put it down, we see the volcanoes and the sun were flat, or the volcanoes have even increased at the very end with Pinatubo in 1991. Naturally, we should have a very stable climate, not seeing the warming. So, if we're good in our way of explaining, we can build something like the Eiffel Tower. You can take one little part in here, shake it a bit, and this thing is stable. It holds together, it's corroborated, not every single element of the Eiffel Tower is cut to 100% precision, but this thing holds up, it's stabilizing itself. A house of cards, which some of the critics particularly want us to believe that the whole climate explanation is a house of cards. Take one card out, and the whole thing crashes. And one card out means, oh, there is an uncertainty in one particular measurement. It simply is not the case. We are over here, there is nothing that fundamentally suddenly can change all of these relationships and explanations. You have to come up with something way better than what is proposed. It might be there, But we can't think of anything that is even a candidate. So, yes, Niels Bohr said prediction is very difficult, particularly about the future. Yet with these tools, if we have gained confidence, we now have to be very careful in saying what parts of this can we use? What part of these tools can we use to really look forward? Even though it's a very difficult problem because it's about the future. What we really have to rely on is that stable framework, a good system understanding. And here are a couple of scenarios where people have said, let's run what-if studies. What if we keep emitting greenhouse gases at a trend, increasing trend, as we have done it in the last 100 years? And what if we start to make reductions in these emissions? What are the changes in resulting overall climate and global temperatures? On the left side, you see these trajectories, the 20th century, up to here, that's where we are, and now the fan of the different possibilities as we go into the future. And these are driven by different emission scenarios, but even when we stop increasing emissions, if we go exactly the same as last year and keep going on forever, we're still going to get a warming. If we freeze current conditions, the system is still trying to catch up. On the right side, you see in the next 20 years the changes, and then by the end of the century, these are temperatures, and they are, I'm sorry, in degrees Celsius and not Fahrenheit. These numbers go at the high latitudes and in the interior of the continents, 3 to 6 to 7 or more, which double that for Fahrenheit is what you have to expect. And even on geologic timescales, on geologic scales, that is recognizable. That's important. And put it in the perspective, this is actually a run that I did a few years ago, a simulation that tried to represent the last 1,000 years, which was driven with all of the forcings, greenhouse gases, but also the sun and volcanoes. And you can see the dominance of the natural factors. The greenhouse gases have hardly changed here, but you see the representation of this red line, how it covers more or less the blue range, which is observations, and how we can reasonably explain fluctuations of the last 1,000 years on a global basis. But that same tool, identical tool, now run for the scenario for the future, shows you not precisely, but the order of magnitude of the change that is to be expected. Yes, it's uncertain of a few elements. It could be a little higher, it could be a little lower. But the scale of the changes is represented about right. So, are there other indicators that we are overblowing, that we are looking for clues that are not really clues? Should we be worried? Emissions are actually, except of 2010, I believe, or 2009, emissions are faster than these assumed scenarios were. So we are already emitting a little faster, so if we're shooting for one scenario, it's at least at the upper end, not at the low end. We have learned about how vegetation is feeding back with the carbon cycle, and we don't think that the ground is taking up as much carbon out of the atmosphere as we have expected before. Ice sheets seem to be melting a little faster than in our models, and in paleo applications, when we go really into deep time, the extreme range in climate that we see in real-world geologic records, climate models have a hard time to reproduce this. We go always in the right direction, but not quite warm enough for the polar latitudes when there was no ice. We, in the climate models, cannot get crocodiles to live above the Arctic Circle. In a climate model world, crocodiles that are documented would not survive in a climate model world. In reality, they do. Models don't always overestimate, so keep that in mind. There is no indication that we're completely overblowing this problem. Yet what we want now is, as I mentioned at the beginning, to go to the regional scale, where actual decision makers, investments have to take place, where we want to give useful information. The global thing is one thing, yes, and it's easy to explain, but what does it mean for you? That's what we try to do with all sorts of applications. And here is just a warning overall that we think, particularly the Southwest, already now under some water stress, but could it possibly get worse? That's what we need to focus on. How good are these climate models in representing the Southwest and its moisture balance? Quick update to IPCC. That was published in 2007, last year for the United Nations conference again in Copenhagen. An update was done, and you see just confirming and even expanding of the IPCC conclusions. There's nothing new. If anything, things are going a little bit more faster than we thought. And here is this outlook, where we really need to work on. If we want to go for these very long-term projections, Doug Numedal mentioned this morning, stabilizing at present levels, or 450 in the future, is not going to be enough if we want to keep the planet below 2 degrees Celsius warming. The most likely level, greenhouse gas level, is probably more like 350 in these climate models. What we need to learn better is how the carbon cycle feeds back. If you get warming in the high latitudes and you get much larger emissions suddenly out of the melting permafrost with carbon fluxes coming out, when the soils warm up, the microbial activity increases, CO2 comes out. It's well measured, and we just don't know the overall speed. These are things we need to pay attention. And the last thing here in this group, rate of change. Has it warmed in the past equally fast as it has in the last 20 years? Yeah, probably at some point, somewhere, something reorganized that had a similar jump, where it was the internal variability or a burst of either greenhouse gases or solar activity that we don't know of, but it is possible. But what we see right now is the warming is happening, and we see the spatial pattern of one particular process. But think about coastal cities. Yeah, 20, 30 years is the overall standard investment time. But very quickly, when sea level keeps rising in a direction of 2 meters, 1 to 2 meters, which are the latest estimates, within 100 years, on top of that come the storm surges. And that's what these cities are sensitive to. So we should not forget that these are substantial changes that are coming, and it could be happening relatively fast. Summary, climate change is happening, and the primary driver of the recent trends is clearly human activity. Changes in greenhouse gases, some changes at the surface as well, but greenhouse gases. The changes are substantial. We can discuss if the last decade had 0.18 or 0.2 degrees Celsius of warming per decade. But if we extend this to 50 years to 100 years, this is geologic scale change. This is not your standard variability that human civilization has seen. It's a big change, and we're causing it. Climate models are now good partners. They have progressed in representing the key aspects, and therefore are good partners at the table to try to understand and predict what things can happen. But particularly for the smaller scales, we need to be a little careful. As I said, limitations. And what we are simply needing to do is to limit our emissions. And as Doug Numedal explained really well, we need to do it the sooner and the faster than we are currently thinking we're capable of. Because of the compound interest, CO2 accumulates in the atmosphere, and we have no tool of getting this thing back out at any useful time. That is the problem. And so we need to do something now. I thank you for your interest, and just show you in the background the challenge. We know what we need to do, yet we need to feed these lights that are trying to come through the darkness here in the slide. These are the energy use of populations that demand the feed, and we need to find a balance between these. Thank you very much. First of all, I say this. Some people say that scientists are under pressure to produce a particular type of results that have to fit or stick to a larger picture. Within NCAR, the National Center for Atmospheric Research, we scientists, we do not get any directives of what our results are supposed to look like. Yet we achieve, or we get all in the same direction of the results. So there is, across the institution where there is climate studies, there is no single signal, single pattern, single event that we would say is counter to that chain of that leads to conviction of greenhouse gases as being the primary drivers. So I am fully independent to say that, and therefore I can also say that when you look at the statements that come out from the National Center for Atmospheric Research, but it's echoed from all of the national science organizations, the American Geophysical Union, the American Meteorological Society, you go wherever you want, the National Academy of Science, the conclusion is pretty much along the lines that I tried to lay out for you here. There is no credible argument that is on the table that might pull a card underneath that overall framework, and we're afraid that it will fall down. There is no such candidate. About the speed and the directions, there are many different ways how individual scientists or individual society members can project these results. They can talk about the drama that is going to happen tomorrow, or they can sit together, as I have tried with Doug Numedal and the School of Mines, which is a really very enriching exchange, and we hope we can push this into the future, to sit down and work with the industry that can help to make this change. And he mentioned this morning a potential that we see, since we do need to make changes right now, if we could work with gas industry to start to replace coal with gas right now, existing technologies, a good partner next to renewables, more jobs, all of this than in the coal industry. We have right now a way to slow down the overall trend, which is all we need from the science side, saying we need to slow down. Eventually, and that's also within a few decades, we can't even use gas in a current way because these emissions are going to be too high. That's my opinion. Some people say this more strongly. Others would say it a little bit more damped. You will get the full spread, but these are personal opinions, and we are not policymakers. We can only provide the information.
And thank you so much.
You're welcome.
I appreciate you.